Okay, so where did we leave off? So we've been trying to learn how to do this thing we call system analysis. Reorient ourselves here. And again, that was, you give me some description of the dynamic behavior of my discrete time system. And we're probably going to be talking about linear time invariant system. So give me some description of that. Give me some input discrete time signal. Maybe give me some initial conditions. And my job is to find what's the output sequence that's coming out. So given this information, what's going to come out for that particular input in that particular system and that particular set of initial conditions. And so far we've got a couple methods. We can use recursion, the table method we did last time, which is literally running the difference equation using the set of inputs and the set of initial conditions in a table form where we're just kind of keeping track of all the signals and all their delayed versions, whatever the difference equation calls for. And that gave us a bunch of numeric values for the output signal. And I said, well, maybe I'd want something better than that. Maybe I'd like an analytical expression, some function of n, y of n is some function of n, and who knows what else. And so far we started on was saying we could actually solve the difference equation for the particular input and the particular initial conditions. And we only got through kind of the setup on that, so today we'll try to take us all the way through. How do we do that? What's the method for solving the difference equation for a particular input, particular set of initial conditions? And then there'll ultimately be another method, which is convolution, which requires a impulse response of sorts, or something we'll call the unit sample response. And that's going to take us a few days to go through, but that's where we're heading next after we do the difference equation. Okay, so there's where we were. And in terms of that number 2, how do we solve a linear constant coefficient difference equation? The method is the method of undetermined coefficients, which is similar to how we solve linear constant coefficient differential equations in continuous time systems. The methodology is the same, it's just adapted for discrete time difference equations. So even though we can break up the solution into a forced response and natural response, we're going to approach it using a different combination that we said was the zero state response and the zero input response. And the sum of those two will give us the total response. And so remind me, what was the zero input response? Those of you who are here, go to watch the video. What's that? Which feels like zero state or zero input. Zero input feels like zero. Feels like input set equal to 0, doesn't it? Yeah. Okay. I think you're right. No. I think so. Let's just take it as a word. The zero input response might be the response to the system when there is no input. And what's it responding to then? The initial conditions, the only thing else it could be responding to, which leaves a zero state response to be the response of the system to just the input, assuming that you started from a 0 state, meaning all the initial conditions were 0, everything the system is relaxed, it's all calmed down, there's no residual stuff going on, it's blank, it's a blank slate, and you're just going to hit it with a new input. So we're separating out the responses into those 2 pieces. And the sum of those would give us the give us the total response. So yeah. So for the zero state response, we set all initial conditions to 0 and use the real input. So it's as if we have a relaxed system. The zero state response, we set the input to 0 and see what's left over from the initial conditions, how that's going to play out in whatever its response that's not finished. So that's leftover stuff. Okay, I'm going to skip ahead on the explanations. We went through that last time. And what we'll do is take an example through this. So an nth order linear constant coefficient differential equation has a known input, a known differential equation form. And what we're going to start with is the thing we call the single input case. And that's where we set all the x terms equal to, well, to just x sub n. So even if I have x sub n minus 1 terms, x sub n minus 2 terms, we're going to ignore those and just have x sub n on the one side. We're going to solve that by finding its characteristic equation, finding its zero input response and its zero state response, and then generalizing for the total differential equation. There's my example. There's the example. So that's the example. We're going to take this example problem through the whole thing. So here's our example. This differential equation, y of n equals x of n, well, that one plus x of n minus 1 minus 1 half y of n minus 1. I'm going to put that up here because we're going to lose this slide in a minute. We want to solve that differential equation for a particular input that's 2 u of n, so that's like a big unit step. It's like this, versus n, 1, 2, 3, minus 1, minus 2. So it's 0 till time, till index n equals 0, then it goes up to a 2, and stays there. The same height forever. So two height step. It's a causal input, and we want to know what's the output, and we'll have some initial conditions, which is that the output at n equals minus 1 is equal to 2. So I've got my system description, that's the differential equation. I've got the input signal described as an analytical function, and I've got my initial conditions. What order system is this? First order system, the highest delay in the n side is a 1. First order system, so I need 1 initial condition to solve a first order system. Okay. So according to the method, I'll back up here, I've got to first solve not the original problem, but the single input case. Single input case. So what would that be? Well, that looks like y of n. Let's bring this over to the other side, plus 1 half y of n minus 1 equals just x of n. It would be the single input case version of our difference equation. And that single input case has a characteristic equation that comes from looking at the left-hand side of the difference equation, rewriting it with a z operator, same kind of z operator we used in our delay blocks in our block diagram. So if I have a y of n minus 1, that becomes, well, it was a delay of minus 1, a z to the minus 1 operating on y of n. So we rewrite our difference equation using this z operator. I have a y of n that isn't affected. I have a 1 half, and it looks like I'll need a delay, a z to the minus 1, operating on y of n. equals just x sub n. Well, in this case, we're going to set that characteristic equation equal to 0. And using these operators, we'll take out that y of n, and we have that's a 1 plus 1/2 z to the minus 1 equals 0. And let me come up higher again so we can see what's happening. So if that's true, this must also be true, 1 plus 1/2 z to the minus 1. That's our characteristic equation. If I multiply everything through by z, I have z plus 1/2 must be 0. So either of these two forms we would say are the characteristic equation. And when I set them equal to 0, I'm finding the homogeneous solution. So we're going to solve this and find the solutions. So z must be, looks like minus 1/2 would be our solution to the homogeneous solution to the characteristic equation. Okay. So in terms of our method, first we're going to start by finding the zero input response. Called the ZIR for short. That's the response of the system to the initial conditions. Okay. All right, how are we going to do that? So we're solving with no input, x sub n is 0. We're going to use the initial conditions. Nope. Then we're going to, after we find the zero input response, we'll find the forced response, then the zero state response, and the total response. All right, let's get into the method. I guess we'll start with that. There we are. So here's the method for finding the zero input response. First, we find the roots of the characteristic equation. And that's what we did here. We create this characteristic equation. We extract it. We set it equal to 0 to find its roots for the homogeneous solution. And in this case, we got that z equals minus 1/2. Then we use our table to tell us the form of the natural response. Zero input response. Let's use the same. And there's our table. So depending on whether this root is real, imaginary, complex, will determine what form, what mathematical form the zero input response takes. In our case, we've got a negative real root. So in this table, that says our zero input response, or anything that's a natural response, is going to be some unknown coefficient times the root itself raised to the n power. Back up there. So we've used that table. We've done step B to give us the form of the natural response, the form of the zero input response. And now we have to find K. Well, how are we going to find K? We're going to need to use that initial condition to find the unknown coefficient. So using that initial condition, y of minus 1 was, what did we say, 2? So if we plug in n equals minus 1, that must be true. And what's minus 1 to the minus 1/2 to the minus 1? So minus 2k must be 2. So k must be minus 1. So the zero input response looks like it's going to be minus 1 times minus 1/2 to the n. And if you like, starting it at n equals 0. So we got the form. The zero input response is a response to initial conditions. There's no forcing function, so there's no forced response. It has the form of the natural response of the system, which is dictated by the system's dynamics, which comes in from the characteristic equation of the system, of the difference equation. So we found the characteristic equation. We found its roots. The roots determine the form of the natural response, which is also the form of the zero input response. And we use the initial condition, the actual initial condition, to solve for that unknown k, because we wanted to know the response of the system to just the initial conditions. So I'll kind of go ahead. Why did I specify to start at 0? Because my input, well, my input started at 0, so that's the n equals 0, so that's the point that I'm interested in. And also, that's the next point after we've defined the initial condition. Okay. Okay with that so far? Yeah. Right. Because this will, because it's negative to the n, it's going to oscillate back and forth, positive and negative. This will just invert it. So we need to keep those separated. Yep. Okay. That's how we do the zero input response. The zero state response, again, we had to start with the single input case. The single input case. Let's switch back to black to make it easier to read. I'm going to come back over here. So now we're talking about the zero state response. Of the single input case. Again, this is the response to just the input with no initial conditions. All right. The form of the forced response is determined by the forcing function, x sub n. What's our forcing function? Unit step. Which is just a constant for n greater than or equal to 0, right? It's a constant. Well, let's see what we do with a constant there. So on the table, we look up the forcing function on the left in the form of the forced response on the right. Now, I'll warn you, there's some asterisks up there we have to watch out for. Our forcing function happens to be a constant, and so it doesn't have an asterisk. We're all right. But what it does say is, if my forcing function is a constant for the time period that I'm interested in, the forced response, I'll use a yf of n to denote that, it's going to be some unknown constant, probably different than this one, unless the system has a gain of 1. So we get the form from a table based on what form our input forcing function is. And then we're going to substitute this forced response into the single input case difference equation. So y forced response of n plus 1/2 y forced response of n minus 1 is equal to x sub n. Y, if we have a constant, well, we know that's a constant. If I move out in time a ways, other than at n equals 0, but if I'm kind of out in there a ways, the previous one will still be a constant. So that's not going to change. And for x sub n, now I put in the actual x sub n, which for n greater than 0, let me put that in. Okay. So I said the force response is a constant. Force response delayed by 1 is also a constant, if you're out far enough. And the 1/2 carries over. The force response needs to be a solution all by itself to the single input case difference equation. So I should be able to substitute it in here with the actual input. And that should let me solve for C. So 3C is 4, C is 4/3. I hope. So that says my force response is that constant 4/3, but I didn't turn on the input until till index n equals 0. So I'll, just for bookkeeping, I'll put that u of n in there too to let me know nothing was happening before that. I can't have a forced response before the system was input because I have a causal system. Questions? Yeah. So if I'm out here at 1, 2, 3, 4, and n equals 4, y of n equals 4 equals 2, right? And at that point, y of n minus 1 is y of 3. That's also 2. So for other than the starting position, the delayed, from out here a ways, the delayed version of the previous sample input is the same value because it's a constant. Now if I had, so for example, y of f, let's look at one of the other forms, right? So if we had an alpha of n, u of n, like I had a force response of c times, I don't know, 1/3 to the n. Right? Then if you ask me what y forced of n minus 1 is, well, that's going to be c times 1/3, and replace n with n minus 1. But in the constant case, I don't have any functions of n in there, so it doesn't show up. Yeah. What is the meaning of the forced response? It's rather like the meaning of life. Those are your Friday. What's the meaning of the forced response? I'm sorry? Or what's the number? I keep shaking them. I guess my podium. Okay, here's my podium. Forced response. All right. So if I just hit this podium and look at its position of the center of it, it's doing this, right? Okay. And if I keep hitting it and then stop, it does some weird stuff, and then it settles into that same kind of pattern. Well, that same pattern it keeps dropping into, that's its natural response. No matter what kind of input I give it, it's going to settle into that sort of response. It dictates the shape of its natural response, its transient response. When I hit it just once, it did something, and then natural response took over. If I keep hitting it, that's a different forcing function. And its total response is a response to my keep hitting it. It keeps on going, keeps on going, keeps on going. Natural response still wants to just do that dying oscillation thing. They're both happening in there. So I'm separating out those pieces. How much of that response was due to the way I'm hitting it? That's the forced response. How much of it was just due to the fact that it always wants to give me the same response because the height, the mass, the distribution, all that physical stuff. Okay? So the natural response is the part that comes from the inherent dynamics of the system. The forced response is only because of the way I'm hitting it. And so that's why the forced responses have the same functional form in general as the forcing function I'm using. If I push it over, well, if I push it over, it moved over and it wobbled. Well, the move over piece, that's the forced response. The wobble's the natural response. Help? Yep. I'm sure it is. Y of F equals. Yeah. I'm doing 228 too much. We are in a discrete domain. There was no T's over there. Can't have a Y of T. Thank you. No, well, yeah, we unsampled the system, went back to continuous time, and I didn't tell you. Sorry. It could happen. It could be. You know, if we're talking about meaning of life, you might have a TARDIS handy. Who knows? Okay. So we've got the forced response. Forced response for the single input case. I'm going to keep reminding. That's the single input case. That's not really the forced response for the total system. I dropped some stuff off my difference equation. I dropped a term off my difference equation. I haven't solved this one yet. I'm still working on solving this guy. What else are we supposed to do up here? Perform a lecture, use stress, traumatized, use hard, try straight, stress, and solve for unknown coefficients. Oh, okay. So, the zero state response, force response is one piece of it. I guess we're going over here. Continuing the zero state response for the single input case. The zero state response for the single input case, so I'll use a 1 there, remind me of that. That's made up of the forced response plus another piece. Ends. Always ends. Discrete time functions. The forced response piece and the natural response piece. I'll say part. Okay. That's what's in the zero state response. That's the response of the system if it didn't have any initial conditions, if it was sitting at rest and I hit it, as we were saying, it's going to move over because I hit it, and it's going to wobble because of its natural response. That's what we're solving for. This guy over here, the zero input response was, I hit it a while ago, and it was still wobbling when I came up to hit it again. So the wobble it was finishing off from the previous time I hit it, that's what's here in the zero input response. There's no input, but it was wobbling when I walked up to it. This zero input response is also a piece of the natural response. It has the shape that comes from the inherent dynamics of the system. It's the transient, the end of the transient from the previous inputs, if you will. Here's the transient of the new input. Yeah.
So if you still understand what our end goal was, like what two parts you're looking to add together in the end?
Ultimately, I want the total response, which is either all of the forced response plus all of the natural response, or all of the zero state response plus all of the zero input response. It's just two different ways to parse the problem. So we could call this yn2 of n. That's a 2. Here's a piece of the natural response is in the zero input response. Here's another piece of the natural response as part of the zero state response. Here's the forced response. That's all in the zero state response. Now I've got to be careful. This piece is incomplete. Even when I solve for it, it's still the natural response of the single input case difference equation. I'm going to have to take this information and promote it, manipulate it so that it's no longer just the solution to this equation, but to this one. That's going to be another step. But that's where I'm going. I want the total response of this difference equation. I can't solve that right away with this method. I got to jump down to this simpler one, find the zero state response of this one. It turns out the zero input response is going to be the same for these two, because the only thing I changed was input terms. I didn't change anything on the y side, anything related to the system dynamics. So when I found this answer, that's applicable to both of these. Right now I'm finding zero state response for the simpler case, and then we'll show you how to take that and make it the solution to this one, so that I can ultimately add the zero state response of this equation to the zero input response of this equation to get the total solution. We're back in perspective? Okay. There's a lot of steps. I understand. We've got to keep them all in perspective. All right. Forced response. I know what that is. I just solved for it. It's over there somewhere. 4/3. Right? It's 4/3 u of n. Flip the page here. And the natural response. What can you tell me about the natural response? It looks a lot like this guy. It looks exactly like this guy, at least in functional form. It may have a different coefficient out in front, but this is the form, the same form of the natural response, the same one we looked up in that first table. It's going to be some minus 1/2 to the n u of n once we get there, but with some coefficient I don't know. Let's call that K2. There's a hand. Question? Oh, this is because here's natural response N1, here's natural response N2, and the total natural response of n, discrete time function, is the sum of those. Yeah, that's probably true. Yeah, it's probably reversed in the notes. I usually use yn1 for the zero input response because we solved for that first. Yeah. Oh, but I will. No. We're looking for this K2, which will give me the natural response piece that's part of the zero state response. And I'm gonna need that information so that I can take this zero state response for the single input case and make it the zero state response for this guy. I've got to get rid of all the unknowns. So how did we find the unknown coefficient over here? We use initial conditions. Oh. So we're going to use the initial conditions. The initial conditions for a zero state response. Let's get this out here for a moment to solve this equation. To find that unknown K2. Come on, Marco. Stay with me. K2. So we're going to solve for this, just like we did over here, using initial conditions, but the initial condition that we use has to be the one that's appropriate for a zero state response. For a zero state response, we're assuming the system is relaxed, which means all the initial conditions have to be zero. Question? Great. So the natural response has a particular functional form, particular shape. When we solved the roots of the characteristic equation, we looked that up and it said, oh, here's the shape. It's a 1/2 to the n with some unknown constant out in front. So anything that's a natural response has this form. The piece that went with the zero input response, we had to solve for this k, and we found, oh, that k was -1. Over here I have another piece of the same response. It has to have the same shape, -1/2 to the n. It has a different multiplier out in front. Right. I want to know what part of the natural response that is due just to the fact that I kicked it with a new input. Here's the part that's due to the fact that I kicked it previously and it was still wobbling. The initial conditions were driving it. Here's the piece that's purely due to the fact that I put a new input in, and it's going to come up with a new response, and I want to know what that piece is. Yeah. I'm just kind of, remember U of T's and how they floated in and out of these solutions? They're floating in and out again. I really don't need them until we get to the generalizing. So, but we can, certainly in the zero state response, this response won't exist until then anyway. I didn't start till n equals 0, so if you'd like to put a UN around it, that's okay. Here doesn't matter. When we get to the next step, I better see some U of N's, and I'll show you why. All right, so we're all back to what we're doing here. Got our perspective again. How we doing? Oh, we're gonna make it. Okay. So we're gonna solve using the initial conditions. So at n at -1, my initial conditions for the zero state response is 0. That's the initial condition that we use to find a zero state response. For the zero input response, we use the real thing, but I want to know what's the response of the system when it started out relaxed. Well, here's how I make it relaxed. I set its initial condition to 0. So we plug in n equals -1 into our equation, our thing here, 4/3 plus K2 times -1/2 to the n -1. And I'll I'll move over here because you're starting to get things blocking your view. And that's going to, here we go again, eraser. We'll use this. So let me copy that back over here. So we have 4/3 plus K2 is minus 1/2 to the n minus 1 has to be 0. I hope. Lied. Not n minus 1 minus 1, right? N equals minus 1. Now, that's better. You okay with that? So I put in the initial condition. I put my zero state response into the proper place for the initial condition. I use this, the appropriate initial condition for a zero state response, which is everything equal to 0. And this I can solve. Minus 1/2 to the minus 1 looks like a minus 2, I think. So that looks like we've got a 2K2 on this side. We got a 4/3 on this side. Is that really what we got? Yeah, we do. K2 must be 4/6 then, which is the same as 2/3, right? So our zero state response for the single input case is going to be my forced response. Here's where it counts now. And my natural response, which we said was K2 plus 2/3 minus 1/2 to the n. Now I'm going to want to say this is only valid for n greater than or equal to 0, because that's when I'm starting up my input. Prior to that, well, at y equals minus 1, here's what the output was. At y is minus 2, I don't know what it was. I don't have information. And I don't really care. Here's what it was before I hit it with my input. As soon as I hit it with my input from then on, here's the zero state response for the single input case. And here's the zero input response. Oh, that was hard. Oh, we have 5 minutes to get there. Okay, what do we do now? What do we do now? We can find, well, if I hadn't gone to the single input case, then all I do is add zero state, zero input, get total response. But we demoted our difference equation first. We got this kind of condition where we got x of n minus 1 stuff on the other side, like this guy, that I got rid of in my single input case. How do we find the response to this system using the response to this system, the single input case? Well, that's when we start playing with linearity and superposition. That's why this only works with linear time invariant systems. If I found the response of a system to x of n, the response of the system to a times x of n is a times that response, right? Let's do pictures. Pictures are good. If one signal x of n gives me a y of n, y1 of n, another x of n gives me 2 times that. If I scale a times x1, I get a times y1, right? That was the homogeneity property, half of linearity. If I add 2 inputs, that was additivity. I add their outputs. And if I add and scale them, I get the same scaling and the same sum of the outputs. That was superposition. If I have a linear system, this is true. It's also true if it's time invariant. If I delay x of n by 1, y of n delays by 1. Okay. So if I put in this combination of inputs, I'm going to get this combination of outputs. And so the way I generalize my zero state response is delay it if I have any delay exabend terms. And if I have any multipliers out in front of them, I will multiply them as well. So if you have this condition where on the right side we have the B0 exabend, B1 exabend minus 1, and so on, the overall zero state response is take that same B0, multiply it by the zero state response from the single input case. And then if I have a B1 exabend minus 1 term, I'll take the single input case zero state response, delay it by 1, and scale it by B1. And so on and so on and so on. Okay? So in our case, I know the solution to this. We don't need this anymore. The zero state response for the general system, which is this guy, we'll call that YZSR of n, is going to be, well, I've got an x of n term scaled by 1, and I have another YZS1 single input case delayed by 1 and also scaled by 1. So I'll get one of my friends there, 4/3 U of n plus, what did we have there? 2/3 times 1 minus 1/2 Kn U of n plus another one, 4/3 U of n minus 1 plus 2/3 times minus 1/2 to the n minus 1 U of n minus 1. Now's why I needed my U of n's at that point, so that we could delay those as well. This is why the zero state response for the general case. Okay. So then the total response, let's call that YT of n for the general case. The real case we came to get is the zero state response of the general case plus the zero input response, which is the same for the general case and the single input case. So it's all of this stuff plus one of these. It looks like minus 1/2 and U of n. All that stuff's going in there, which I won't write for time. Okay. Only took 45 minutes to get through one problem. Isn't this a great method? We'll review that. We'll cover a couple special cases on Wednesday, and then we're going to move on to how we use these to find things like unit sample responses to set us up for convolution. We're going to get through all those methods. So we'll do a quick review next time, make sure we got all the facts and figures straight, and take another example partway through with some special cases. So stay tuned.